Hi everyone. This is the second class of the linear algebra. From me, my name is Xinjie, and today I will talk about the quadratic form, and it will cover four parts. The first is the orthogonal matrix. The second one is the diagonal form and signature. And the third part is the transformation into a diagonal form, and the fourth part is the positive definite matrix. So in this course, two books are the references. The first one is the second course in linear algebra, and the second book is Introduction to Linear Algebra, the 5th edition. And these are the covers of these two books. So what is quadratic form? Quadratic form is in n variables, that is a homogeneous polynomial of degree 2 in n variables. So this equation here, or this function here, we can see that there are n variables from x1 to xn, and each term has a degree of 2. So such as here, x1 squared, x2 squared to xn squared, and in other terms, such as x1 times x2, the degree is also 2. x1 times x3 is also 2. And here, a11 to ann, they are all coefficients, and they are all, if they are all real numbers, then it is called a real quadratic form. So we suppose that these two coefficients are the same, then this equation will hold. So basically, we split this term into two terms, and that is used to write in matrix terms. So here, from x1 to xn, this factor is the transpose factor of x, and this is the associated matrix. And here we can see that because aij equals to hai, so basically a12 equals to a21, and similarly a1n equals to an1. So the matrix is a symmetric matrix. And the rank of the quadratic form, it is the rank of the associated matrix A. So this matrix. Okay, then let's see some examples of the quadratic form. The first one here, it contains three variables. So x1 squared plus 2x2 squared plus x3 squared plus 2 times x1 x2 plus 4x1 x3 plus 6 x2 x3. So to write in the matrix form, this part is easy. It is a transpose vector of x, and this is the vector x, but for the associated matrix. In the diagonal line, it is also easy, just the coefficients of the x1 square, x2 square, and x3 square. So 1 to 1 here. But for other parts here, like so basically these two are half of the coefficient of x1, x2, and these two are half of the coefficient of x1, x3, and these two are half of the coefficient of x2, x3. So we can see that the index here, this one is like A21, and this is A12. So the index is 1 and 2. So these two are corresponding to the coefficient here. And these two are the indexes of these two are 1 and 3. So they are corresponding to this coefficient. And similarly, these the indexes of these two are 2 and 3. So they are corresponding to this coefficient. And remember to divide the coefficient into 2. And similarly, in this case, there are 4 variables, so it's a bit more complicated. But this factor and this factor are still just x. And this is the transpose factor of x. And in this line, in the diagonal line, still just the coefficient of the x squared, xi squared. So since the index here is 1, 1, so it is 3, and this is 2, 2. But here the term x2 squared is missing, so the coefficient is 0. Here is -1, and here the index is 4. 4, 4, so it is the coefficient of x4 squared. And again, other elements are just the corresponding coefficient divided by 2, such as here the indexes are 1 and 2. So we look at this coefficient, and -5 divided by 2 is -2.5. And other elements are the same. And then the orthogonal matrix, the length. So the length of the vector, it is written in this form. So the length is the square root of the inner product. Here, the inner product of the vector itself is just the square of each element, the sum of the square of each element. So a1 squared plus a2 squared until an squared. And then the length is the square root of the inner product. So it is this term. And the length will always be greater or equal to 0. And if the vector is not a 0 vector, then the length will always be positive. Only the 0 vector has a length of 0. Let's look at some examples. The first one, the length of the vector alpha 1, 2, 3 equals to the square root of 14. Basically, we just apply this formula. So the sum of the sum of the square of every element. So 1 square plus 2 square plus 3 square is 14, and the length is just the square root of the inner product. So it's square root of 14. Similarly, here it is also 14, even though these two factors are not the same. And the length of the vector, of the 0 vector, is just 0. And then the unit vectors. The length of a vector alpha equals to 1. Then this vector is a unit vector. The normalization. So how can we maintain the direction but change the length into 1? In this case, we will use the normalization. And basically here, when the beta is not a unit vector, but we want the unit vector with the same direction with the beta, then we will use this equation. Basically, just the vector beta divided by the length of itself, and the alpha here, it will be the unit vector. For example, the unit vector with the same direction of the vector beta is here. Basically, apply this formula again. So in the last slide, we know that the length of the vector 1, 2, 3 will be square root of 14. So alpha will be this vector. And the orthogonal okay, then the orthogonality. If two vectors are non-zero vectors, v and w, then the angle contained by these two vectors are the inner product of these two vectors divided by the length of the product of the length of two vectors. So basically this formula, and we can have the cosine theta. The dot product is 0 when these two vectors are perpendicular to each other. In this case, the theta will be 90 degree or pi divided by 2. So the cosine theta will be 0. And we can look at this graph here. So this vector is the vector v. If the vector w is this vector, then they are perpendicular to each other. So the angle here is 90 degree. But if w is this vector, then the angle is less than 90 degree. And v times w will be greater than 0, because the cosine theta will be greater than 0. And since the lengths are always positive, then v times w will be positive as well. And if w is this vector, then the angle will be more than 90 degree. Then the cosine theta will be less than 0, since the lengths are always positive. So the v times w will be less than 0. Okay, then we look at some examples. The angle theta contained by these two vectors, how to calculate it? We just use this formula. And the inner product of these two vectors, basically just the sum of the product of the corresponding elements. So 1 times 0 plus 0 times 1 plus 1 times 0. So the numerator is 0. So actually we don't need to calculate the length. It is already 0. So the cosine theta is 0. Then alpha is perpendicular to beta. And the second example, to calculate the angle contained by these two vectors, alpha and beta. But in this time, the inner product is not 0 anymore. So 1 times 1 plus 0 times 1 plus 0 times 0. So the numerator is 1. And the length here the length of the vector alpha is just 1, and the length of the beta is 1 square plus 1 square plus 0, and the square root of it, and it will be square root of 2. So theta will be 45 degrees, or pi divided by 4. Okay, then orthonormal vectors. The vectors alpha 1 to alpha n are orthonormal if alpha I times alpha j equal to 0 when there are different vectors. So they are perpendicular to each other, and if alpha I times alpha j, if I equals to j, so when every vector times the vector itself, it will become 1. So basically, every vector in this list is a unit vector. So the length is 1. A matrix with orthonormal columns is assigned the special letter Q. We will use this in later. And in this case, the transpose matrix of Q times Q will be the matrix I, and I here is this matrix, only the diagonal. So all the elements in the diagonal line will be 1, and other elements will all be 0. So basically, elements in this triangle and this triangle will be 0, and elements in this line will be 1. And this is from basically this. From this we can calculate this. And then the orthogonal matrix. If Q is also square matrix, then this not only this equation holds, and we can get this equation. So the transpose matrix of Q equals to the invertible matrix of Q. And Q is an orthogonal matrix. The columns and rows of orthogonal matrix are all unit vectors, and they are perpendicular to each other. So basically, the length of every row or every column is 1, and they are perpendicular to each other. So the vectors of every rows or every columns, the list of these vectors are orthonormal. Okay, then we look at this process. So it takes a linearly independent list, alpha 1 to alpha n, and constructs orthonormal vectors, gamma 1 to gamma r, using the following algorithm. So this list of vectors are orthonormal, but alpha 1 to alpha n are just linearly independent. Okay, and the first step is beta 1 equals to alpha 1. And then for each, for the other vectors, we have beta k equals to alpha k minus alpha k times beta 1. So this is also the dot product. So this is a number. And here, this is the the dot product of itself and also a number. So alpha k minus a number times beta 1 minus a number times beta 2 minus a number times until a number times beta k minus 1. And so the right side is still a factor. And then after these two steps, we will have that every two vectors in this list are perpendicular to each other, but they are not all unit vectors, probably. So we have to normalize all vectors. Basically, just divide every vectors beta divided by the length of it. Okay, then let's look at some examples. The first one, find orthogonal vectors, gamma 1, gamma 2, gamma 3, by the process we talked about before from the vectors below. So these three vectors. And the solution, we just use the steps, follow the steps in the last slide. Beta 1 equals to alpha 1. And then beta 2, apply the formula. So alpha 2 is this vector, and alpha 2 times beta 1, alpha 2 times beta 1. So here 1 times 1 plus 1 times 1 plus 0 times 2. So it will be 2. This will be 2. And beta 1 times beta 1. So it will be 1 squared plus 1 squared plus 2 squared. So it will be 6. And 2 divided by 6 times the beta 1. Beta 1 is 1, 1, 2. This vector. And then just simple calculation. And then we will have the answer of the beta 2. And then beta 3, similarly, we also apply the formulas. Here, alpha 3 is this vector. Alpha 3 times beta 1. So 1 times 1 plus 1 times 0 plus 4 times 2. So it will be 1 plus 8 will be 9. So the numerator will be 9, this one. And then the beta 1 times beta 1, we already know that is 6. And the beta 1 will be 1, 1, 2, this vector. And then alpha 3 times beta 2. Alpha 3, this vector, beta 2, this vector. So 1 times 1 plus 0 times 1 plus 4 times minus 4. It will be 1 minus 4. It will be minus 3. And then times 2 over 3. So it will be minus 2 here. So the numerator is minus 2. And beta 2 times beta 2. So it will be 1 squared plus 1 squared plus minus 1 squared. So it will be 3. And 3 times 2 over 3, it will be 2. Okay, so here is a typo here, I think. So here it will be, oh, right, that is right. It is not wrong. So it is a common mistake. And here we have to multiply the 2 over 3 square. So it will be 3 times 4 over 9. So it will be 4 over 3. So that is correct here. Okay, I will repeat it again here. beta 2 times beta 2 here. So we can calculate this first. So it will be 1 squared plus 1 squared plus minus 1 squared. So it will be 3. And then times 2 over 3 squared. So it will be 3 times 4 over 9. So it will be 4 over 3. And then the beta 2 here is this factor. And after the calculation, we will have this answer. And after that, we have to normalize the beta 1, beta 2, and beta 3. So divided by the length of the of each factor. And then this is the final answer, gamma 1, gamma 2, and gamma 3. And they are orthonormal vectors. Okay, then diagonal form. So in the diagonal form, only the square terms are left. So the mixed terms are eliminated. And if it is written in matrix terms, and the x factor are still the same, but when we look at the associated matrix, we'll find that only the elements in the diagonal line are left, and other elements are all 0. But of course, A1 to AN, some of them can be 0. And then the positive index of inertia, numbers of coefficients that are positive in the diagonal form. So basically, how many numbers are positive in this line. And negative index of inertia, numbers of coefficients that are negative in the diagonal form. So basically, still, how many numbers are negative in this line? Okay, then let's look at some examples. The first one here, so the coefficients is 1, minus 2, and 3. So we can see that in the diagonal line, 1, minus 2, and 3. And other elements are all 0. And the positive index of inertia is 2, 1, and 3. They are positive. And the negative index of inertia is 1, minus 2. And then the signature. It refers to the coefficients that are 1, 0, or minus 1 in the diagonal form. So basically here, the A1, A2 to AP, the coefficients only have three options, 1, 0, or minus 1. So it can be written as this form as well. And here, the A1 to AP are all 1. And the AP plus 1 to AP plus Q are also 1. But the coefficients here are all minus 1. So P is the number of coefficients that are 1. So basically A1 to AP are 1. And then Q, numbers of coefficients that are minus 1. So here, so this line, the coefficients are all minus 1, but still AP plus 1 to AP plus Q are 1. and n minus the sum of p plus q, that refers to the number of coefficients that are zero, because the coefficients are zero, so the square terms are eliminated from this equation. Okay, then congruent. Let A and B belong to well, A and B are a matrix with dimension of n. Then A is congruent to B if there is an invertible matrix X such that this equation holds, and S is also a matrix with dimension n, and ST is the transpose matrix of X. And this holds. If this holds, then we say that A is congruent to B. Okay, and there are some properties here. A is congruent to itself. That is easy. So we can find an invertible matrix, just E. So only the diagonal, so only the elements in the diagonal line is 1 and all other elements are 0. So E here. And the transpose matrix of E is itself. So it will be E times A times E. And it will be still A itself. So so we can find an invertible matrix E to make this whole. So we can say that A is congruent to A. If A is congruent to B, then B is congruent to A as well. So basically we just times S as invertible matrix of S in the right on both sides. So here as invertible square, the invertible matrix S here, and here it will be the invertible matrix of the transpose matrix of S here. So ST minus 1, and we time these two matrices on both sides, and it will become A equals to this form anyway. So it will A equals to a matrix, the transpose matrix of S minus 1 times B times S minus 1. So B is congruent to A as well, or I can write it down. So basically S minus it's like times ST times A times S minus 1 will equal to ST minus 1 times B times S minus 1. So this part will be just A. And then it can also be written as S minus 1 T. So it will be the transpose matrix of S minus 1 and times B times S minus 1. So it's actually the same with this equation. So we find an invertible matrix S minus 1 here, and satisfy this equation. So B is congruent to A as well. Okay. Then if A is congruent to B and B is congruent to C, then A is congruent to C. Basically the similar logic. You can prove it yourself. Then the transformation into diagonal form. After transformation, this transformation, so X here is a vector and Y is a vector and S is the matrix. The quadratic form will be transformed into quadratic form of, so using Y. And here as the transpose matrix of X times A times S will equals to B. So basically we just plugging this into this. For any quadratic form, there must be an orthogonal transformation. X equals to Qy. So Q here is an orthogonal matrix that can transform the quadratic form into diagonal form. In other words, for any real symmetric matrix A, there must be an orthogonal matrix Q that satisfies this equation, where D is a diagonal matrix. So after we times the Q, the transpose matrix of Q and the Q on two sides, and we will have the diagonal matrix D. Okay, some examples here. The first one, transform this quadratic form into diagonal form. So first, we write down the associative matrix. Still, we look at the indexes and write down the elements, 1, -1, 2. And then only the term x2 times term 3 has a coefficient. So we divide it in by 2. So it will be 2 in these two elements, and other elements will be 0. And then we will have to calculate so we have to calculate the eigenvectors or eigenvalues using this. I think my colleague will cover this part, so I will skip to explain how to calculate the eigenvalues. Basically, we'll just use this formula to calculate the determinant of the lambda times E minus A, and to solve the value of lambda, and we will have the eigenvalues, and they will be usually the number of the eigenvalues will be the same with the dimension of the matrix. So there are 3 eigenvalues in total, but sometimes the eigenvalues can be the same, like 1, 1, 1 in this case. After that, when lambda equals to 1, from this equation, we can solve the eigenvector. So here is still the using some elementary transformation, and then we will calculate the eigenvector alpha 1 equal to 1, 0, 0. So we assume x1 equal to 1, and then x2 and x3 we can calculate it, and they'll be 0. So the eigenvector, the corresponding eigenvector alpha 1 will be 1, 0, 0. And then we have to calculate the other two eigenvectors that are corresponding to the other two eigenvalues. And after the calculation, the same logic, we have the alpha 2 and alpha 3. And after that, we have to normalize these three eigenvectors. And then we will have the orthogonal matrix Q here. It consists of three vectors, just gamma 1, gamma 2, and gamma 3. And we set the x equals to qy. So this is to transform the quadratic form into the diagonal form. And here, we just plug x equals to qy into the diagonal, the quadratic form. So here we have this equation here. And the coefficient of the yi will be the eigenvalues. So here we can see that it will be 1, 3, and -2. But remember, the eigenvalues should be corresponding to the coefficients. So if in the matrix it's like gamma 1, gamma 2, and gamma 3, then the coefficients here should be the eigenvalue that are corresponding to these three vectors. But if the matrix is gamma 3, gamma 2, gamma 1, then the coefficients will be -2, 3, and 1. So they're different. And then we can calculate the matrix of these three, and it will be in this form. So basically only the elements in the diagonal line will have non-zero values, and other elements will be 0. And here still it is corresponding to the coefficients here. So 1, 3, and -2. And another way to transform into diagonal form is completing the square. Any quadratic form can be transformed into diagonal form using completing the square method. So in this method, invertible linear transformation, so this transformation will be used. And C here is the invertible matrix. Okay, so in this example, and transform this quadratic form into diagonal form. So the solution here, the first step is to complete the square with regard to x1. So we first just complete the square. So here we can see that so basically here, the first two terms are all terms that contain x1 in the quadratic form. So we have to complete the square first using these two terms. And after that, we plus the terms that are left. So 3x squared, x2 squared plus 5x3 squared minus 8x2, x3. But since here we plus a 2x2 minus x3 squared, so this term, since we plus this term to complete the square in the first term here, so we have to minus this term. And after the calculation, we will have this left. And the second step is to complete the square with regard to x2. So basically, we have to complete a square using x2 squared minus 4x2 x3. And after the calculation, we have these terms left in the right side. So we assume that y1 equals to x1 plus x2 minus x3, and y2 equals to x2 minus 2x3, and y3 equals to x3. Then we can substitute these terms with y1, this with y2, and this with y3. And this quadratic form will become the diagonal form. So 2y1 squared plus y2 squared minus y3 squared. And to get this, we have to calculate the answer of the x1, x2, and x3 using y1, y2, and y3. And after that, the associated matrix in the first, so the quadratic form, we can write down the associated matrix 2, 3, 5, and 4 divided by 2. So 2 here, minus 4, minus 2 here, and minus 8, minus 4. After linear transformation, so this transformation, so basically this is the same thing with this one. So x1 will equals to y1 minus y2 minus y3. So y1 minus y2 minus y3. And similarly in the left part. And then we have this equation here. So the quadratic form is transformed into a diagonal form. And similarly here, C, the transpose matrix of C times the associated matrix A times the C will become this matrix. And the elements in the diagonal line is just the coefficient of the diagonal form. So 2, 1, and minus 1. And in this equation, x equals to cy, so we plug in here, so it will become the transpose factor of y times these 3 matrix times y. And then these 3 matrix will be this matrix. Okay, the last part is the positive definite matrix. for all non-zero and vector x, if the quadratic matrix, the quadratic form is positive, then the corresponding associated matrix A is positive definite matrix. Here are some examples. Quadratic form x1 squared plus x2 squared plus x3 squared for any non-zero and vector, f will be greater than 0. Because as long as the x1, x2, and x3 are not all 0, then the f will always be positive. So the associated matrix A here, this matrix is positive definite matrix. And here are some properties of the positive definite matrix. If A is positive definite matrix, then positive index of inertia of A equals n, so the dimension of the matrix. So basically, all the elements in the diagonal line are positive. And the second one is A is congruent to E. And the third one, the matrix A can be written as a product of two matrices. Here, the transpose matrix of D and the matrix of D, where D is an invertible matrix. All eigenvalues of A are positive. Basically, this is similar to this one. And the last one, all leading principal minors are positive. Assume the matrix A is has the dimension of n. Then A11, so this one will be positive, and this determinant of these four elements will be positive, and it will continue until the determinant of A will be positive. So all leading principal minors are positive. Here are some examples. Whether the associating matrix of quadratic form, this form is positive definite matrix. So first we have to write down the associated matrix. And there are three solutions in total. The first one is to calculate the leading principal minors. In this case, it is easy to use this method because the dimension is only 3. So here still you have to be careful with the indexes, the coefficients 2, 5, 5, 2, 5, 5, and the others you have to be careful. And then the leading principal minors 2 is positive, and this for the determinant of this small matrix 2, 2, 2, 5 it is 2 times 5 minus 2 times 2. So it will be 6, and it is positive. And the determinant of the matrix A itself, after the calculation, it will be 10. I think my colleague will also cover how to calculate the determinant, and I think so I will skip how to calculate the determinant. So this matrix is positive definite matrix. And another method is to calculate the eigenvalues. So similarly here, we just use the lambda times E minus A and calculate the determinant of this matrix. And then we can calculate and this will be 0, and we can calculate this equation. So the eigenvalues are 1, 1, and 10. So here I missed something here. It should be equal to 0. And then after the calculation, the eigenvalues are 1, 1, and 10. So all eigenvalues are positive. So the matrix is a positive definite matrix. And the third method is to complete the square. I think this is a bit complicated actually, but I will show you how to use it anyway. So the first step is still you have to complete the square using all terms that contain x1. So 2x1 squared, 4x1 x2 minus 4x1 x3. So these 3 terms you have to complete the squares first. And the left, you can just leave it here, the 5x3 squared, 5x2 squared, and minus 8x2 x3. And since here, you plus 2 times x2 minus x3 squared, so you have to minus this term in the end. And then the second step is to complete the square with respect to x2. So 3x2 squared minus 4x2 x3. And then the left term is the x3 squared. So we know that the positive index of inertia p equals to 3 because all coefficients are positive, 2, 3, and 5/3. And the negative index of inertia q is 0. Since p equals to n, and the dimension of the matrix equals to 3, the associated matrix is positive definite matrix. Okay, that's it. Thank you for listening.